Hi, this video is going to be about periodic trends and how we can use the periodic table to make an educated guess about various elements or properties that an atom is going to have. So like the first one here, we can talk about atomic radius, or we can look at the table and figure out how big an atom is going to be. We can look at its most likely charge. So when an atom bumps into another atom and they think about exchanging electrons with one another, is an atom going to lose an electron or gain an electron, and how are we going to know? There's also another property called electronegativity, and that's a measure of an atom's ability to steal electrons from other elements. And then lastly, we're going to take a look at the trend in ionization energy, which is a measure of how protective an atom is of its own electrons. So if it has a high ionization energy, it means it really wants to hold on to its own electrons, and you'd have to work really hard to steal them. And if it has a low ionization energy, that means it's more or less willing to just give those electrons away. So the first thing we're going to take a look at is, in this video, is atomic radius and most likely charge. And we'll do a future video about electronegativity and ionization energy. So here are some values I pulled off of Wikipedia for atomic radius. And I stuck the atomic radii in the table so that each atom, it's listed with its size, its radius. So this would basically mean that hydrogen has a radius of 53 picometers. And a picometer is 10 to the minus 12 meters. So we're talking extremely small here. If we look at the general trend, if we go down a family, this 53, the radius of 53, goes to 167, a 190, 243, 265 to 298. So if we were going to take a look and say, what is the general idea as we go down the table like so, we could say that generally atoms at the top of the table are small, and atoms at the bottom of the table are larger. Okay, so let's see if that holds on the other side of the table. Helium starts out with a 31, it goes to 38, and it increases all the way up to 120. So it definitely holds for the right side of the table, and if we just took a random one in the middle, 67, 11, 125, 154, it holds. So this general trend of being small at the top and big at the bottom is going to hold. So let's take another look at a second trend here, and let's take a look as we go across the table this direction. So as we go to the right, what's generally happening in any period as we head that way? Well, we can see that we start out with lithium and it's got a size of 167, and that drops to 112, and it eventually drops when we get to neon all the way down to about a quarter of its original size. It's at 38. So at the top of the table, it looks like we start out big and we get smaller as we go across. Does that hold at the bottom of the table? So let's look. We start out about 300, a 298 here, and we're steadily dropping, and we wind up about a third lower at 120 over here. So in general, we can say that the size of an atom gets larger as we head to the left and as we head down. So I'm going to erase all the stuff that we've written here, and I'm going to say that this area is big and this area of the table is small. Oops, sorry for that T there. And that our general trend is from lower left to upper right, we are going to head and get smaller and smaller and smaller as we head that direction. So is that true? 298, 219, 136, 96, 42, 31. It's perfect. So if we go the other direction though, so let's take a look at this. And I want to show you what's happening as we head the opposite direction. So let's take beryllium for instance. If we head down and to the right, we can get to silicon, which has effectively the same radius, and then arsenic has effectively the same radius, and iodine. So when we head this direction, we're actually almost maintaining the same radius. So heading from the upper left to the lower right, we don't see much change at all, because as we head to the right, we're getting smaller and smaller, but as we head down, we're getting bigger and bigger. And so a move to the right and down actually cancels out. We get approximately the same radius. So the next question is why? Why is this occurring? So let me take a look at my next table here, which is let's take a look at a single family and figure out what's going on. So we're going to go back to the Bohr model, and we're going to draw a Bohr model for hydrogen that has one proton. It's got a nucleus, and it's got one ring with one electron in it. Lithium's got 3 protons, so we'll draw our nucleus, and that means we're going to need 3 electrons. Now, according to Bohr, we can only put 2 electrons in the first level, so we're going to need a second level to put our 3rd electron in there. Sodium's got 11, so going with Bohr again, we're going to have a nucleus with 11 protons. We'll have an inside ring with 2, then we'll have a second ring that has 8 electrons, and we're going to need a 3rd ring that has 1 electron in it. So as we head down the table, you can see why the atoms are getting bigger. It's because we're getting more rings. So as we head down, we get more rings, more energy levels. And more energy levels equals bigger size. So far so good. But that won't explain another move that we're going to make, which we're going to explore right now. So let's say we go to the next slide here. Why do atoms get smaller as we go from left to right? So in this case, let's take a look at it. Let's draw lithium again. Lithium's got a nucleus with 3 protons. It's got 3 protons. So it's going to have 3 electrons. I've got my inner ring with 2 and my outer ring with 1. And I'm actually going to write in that it has 3 protons right here. Okay, and the reason I'm going to write that in is because these 3 protons are going to pull on these 2 electrons and pull them in toward the center, and it's going to pull on this 1 electron and pull it toward the center. Now let's go to the other side of the table, and we're going to look at neon. Neon's got 10 protons, so we're going to need a nucleus, and we're going to put 10 protons in there, and we're going to need to put a ring around it that has 2 electrons, and another ring around it, let's see if I can draw this a little smaller, that's got 8 electrons. So we've got 8, 2, and 8. So when we go from left to right, the number of rings stays the same. It's got 2 energy levels here and 2 energy levels over here. So up here I'm going to say same number of energy levels. But the difference is the inside. On the inside here, lithium had 3 protons trying to hold all these electrons, and over here we've actually got 10 protons holding this whole mess together. So why does that make a difference? Let's say we had 3 magnets. Those 3 magnets are able to pull on 3 electrons pretty strongly. But if we had 10 magnets, the pull would be even stronger, and these electrons are going to get pulled in toward the center, shrinking the rings down, making them really tight. So overall, in our overall thing here, we said that as we headed down a family, the atoms got larger because we added more rings. But when we go across from left to right, the atoms get smaller because our nucleus is getting stronger, and it's able to better pull those electrons into a tight ring. Okay, so that explains our most likely charge. We're going to take a look at one more trend now, and that is that explained our radius, and now we're going to take a look at most likely charge. So let's erase our old stuff here and take a look at the most likely charge trend. Our trend in most likely charge is going to be that our first family, family number 1, takes a +1 charge. And family number 2 takes a +2 charge. Family 13 takes a +3. And I'm going to skip number 14 here for a second, and I'm going to start all the way over here at 18. So in family 18, we get a 0 charge, because these are our noble gases, and they don't want to react at all. Family 17, 16, and 15 follow an also easy pattern where they go -1, -2, -3, and then we're here. So carbon actually marks our middle point where the two trends meet. So these elements here are tending to gain 1 as they get their charge, and these elements over here are tending to lose 1, or actually gain an electron, as it were, but get a -1 charge each time we take a step to the left. So the question is why? What's going on? Well, lithium, we've already said, has 3 electrons, 2 in the middle row or shell and 1 on the outer shell. And so since it is so far from being a noble gas, it's only got 1 valence electron out here, it is willing to lose that electron, get rid of it, and take on a +1 charge. Where over here, fluorine has it's got 9 electrons. So it's got its nucleus, it's got a ring of 2, and a ring of 7. And since it's got 7 in the outside ring, it's actually going to try and pull in an electron from somewhere else, pull it in, and that would give it 8 electrons, which would make it a neon. It would be called isoelectronic with neon, meaning it has the same outside as neon does. It would have a perfectly filled outside shell. And we could do the same thing with oxygen and nitrogen and carbon by looking at the Bohr model, trying to figure out if it would be easier to gain electrons to become empty or full, because remember, we're always talking about atoms having empty shells or full shells, or sometimes, depending on the situation, we might want a half-full shell or a half-full orbital. Okay, so that's a pretty easy trend. You can see that as we go down the family, that very little happens to the charge. +1, +1 all the way down. Over here, -1, -1, -1 all the way down. And the only difference we would see is in the middle. We actually see that these can be plus or -4, but the bottom ones here always tend to take +4. And that goes back to what we were talking about earlier in the week, which is that underneath this jagged line here, if we take a look at this line right here, this is the line that separates metals from non-metals. And in general, these metals down in this section around in here want to lose their electrons. And so the reason we're making a switch over when we go from silicon that could gain or lose to germanium and tin and lead all losing is because these are all metals, and metals tend to lose their electrons. So although a -4 might be a possibility, it's not going to happen in these cases. So good luck with these trends, and tune in for the second video where we look at electronegativity and ionization energy.